So this is just to recall what we have discussed so far in the differential calculus portion, unit 2. So these portions we have discussed already. And then we have also defined the limits, continuity and partial differentiation for several variable calculus. We have seen the total differential, then Euler's theorem and generalization. In the last class, we have also seen the change of variables using the Jacobian. How do we calculate when the function is dependent on intermediate variables and they are also function of some other variable. Now today we are going to discuss one important topic, which is again it will be the concepts will be useful for your throughout your life. Yes sir. How do you find maxima and minima for several variable functions? In case of one variable case, we have seen fx, find the minima and maximum of y equals to f of x for given any function where x belongs to, for example, that domain. In the particular domain, this domain can be one particular interval. This domain can also be the real number set, the whole real number line. Now what will happen if we have z equals to f of x comma y? So how do you, for this, if this is a single variable function, then we have seen that how do we calculate the derivative. First we calculate the derivative and we will make it 0. To find, here we will find out at that particular point, for example this point, then find out this value, or not that, after making this derivative 0, get the values of x equals to some x naught, okay, where the point is x equals to x naught is a stationary point. Stationary point are those points where the derivative is 0. Okay, then we try to find out the double order, the second order derivative. Okay. F double dashed x naught, whether it is positive or negative. Depending on that, we decide whether it is maximum or minimum. So this is just to recall what we have discussed in the our school level mathematics. Now, since you are in the college, so you need to study several variable case. What will be the, for example, f of x to the x comma y, x to the power 4 plus y, for example, y cube. What will be the maximum and minimum point for this case? Or it can be also like w equals to x to the power 4 y cube or plus z square. What will be the maximum and minimum for this function? So there we'll use the concept of partial derivatives and then we'll try to locate. For example, if you if you remember, when we have the derivative equals to 0, then the tangent at that point will be parallel to the x-axis. But here we have a plane. For several variable case, we have a plane. The tangent will be, so both the tangents will be then parallel to the x-axis. In fact, the tangent plane will be parallel to the x-axis. That's the meaning. So just to recall, what is the meaning of the definition? If you follow the definition of a maximum point, then x naught is said to be maximum point if it satisfies this relation, that f of x naught will be greater than f of x for all the x values. Similarly, it is said to be minimum point if that f of x naught is less than all the f of x for all x belongs to the set. There is a domain. Now, in terms of derivative, we have seen that in terms of derivative, we actually write if x naught is said to be a maximum point if the derivative, if the second order derivative at this point is less than 0, and it is a minimum point if the second order derivative is greater than 0. Okay. Now, if you look at here, this is local. Now, why this concept of local maxima and minima? Because if this is our limit a to b, okay. Now the question is, what is the maximum point? What is the here? In fact, here there are several uh, maximum points. At the same time, several minimum points. So these concepts, or actually, there comes the concept of global and local maximum. Extremum, let us say extremum. If you consider this interval, only this interval, then this is our maximum. And if you consider this interval, then this is our minimum. But if you consider overall the total domain, then this is our maximum. So this should be called as local, or this local minimum. In fact, in this region, this is our local maximum. If you consider whole the region, then this would be global maximum. So this is global maximum. The concept of local and global maximum is actually very important, because this is a simple case in two-dimensional figure. There are functions which multiple peaks and multiple values will be there. Okay, so if you just look at the geometry, observe the geometry. For example, if you look at the interval here, for this function f of x equals to x square, and at x equals to 0, if you consider x naught equals to 0, here what you see, f of 0 equals to 0, and if you take the right hand side 0.5, so this is 0.25, which is greater than 0 f value. Also, if you take minus zero point 0.5, then also you get greater than 0. So if you remember, f of x naught is a minimum point if it is less than all the values for all x belongs to yes. So this relation will satisfy. Now this is not only true for these two values. If you take any such interval, minus epsilon to epsilon, okay, in this neighborhood, so there also you will see that this f of 0 is minimum than the other all the values, and this is true for all other values. So look at the geometry. Then if you try to draw the functional value at here, and here it will be like this, and this is greater than this value f of 0. F of 0 is 0. This is not only that, here also you take this 0. So in the neighborhood, you take, this is a neighborhood, you can call neighborhood of 0 because it contains 0. So this is minus, this is plus epsilon, this is minus epsilon. If you take, then you can see that this is actually that f of 0 is less than all other values. So when we have a minimum value, then f of 0 is the minimum value of the fx in the neighborhood of x naught. So this is from the geometry. Okay. Now if you think about the maximum point also, there also you can see, if you take this function value, this functional value, and this is our value. So this f of x naught is greater than this one and this one also. So similarly, we can say that if in this neighborhood, so minus epsilon to plus epsilon, if you think this one, then it will satisfy this relation. This only one type of inequality, either less than or greater than type will be there. But if you think about other function, fx equals to x cube, and then you take f of 0 equals to 0. But if you think about the point 5, f of 0.5 is actually 1.125, which is greater than f of 0. And here, if you think about this, this is less than f of 0. But if this is a minimum point, then both these inequalities will be true. For this case also, you will have this. But if it is a less than type, then it will be only one type of inequality. Okay, so what happens? This point for this function x naught is neither a maximum point nor a minimum point. Okay. Now this particular point is called saddle point, neither minimum or maximum. In fact, this is related to point of inflection. If you remember, when we have discussed the convexity, concave, upward, and downward, if it is not, then what do you say? We say that point of inflection. So what happens here is actually from f of 0, the curve is actually the functional value increases, where this is decreases. This is decreasing and here it is increasing. So if we have such situation, then this point is said to be saddle point. In fact, you will be amazed to know that there is a beautiful application of saddle point. But that we'll discuss just a couple of minutes later. Till then, let us discuss some more fundamental things, which are actually, if you remember, the function f of x y is given, then you calculate fx partial derivative, second order partial derivative. At the same time, you mixed derivatives you calculate, and also you try to calculate the functional values f of y and f of say part second order derivatives. Okay. Now, if you define a matrix whose entries are actually the coefficients of the partial higher order derivatives, second order derivatives, matrix of, define a matrix of second order partial derivatives. Then we can see this one of this form. Now, as you can see that this matrix is actually symmetric matrix. Why? Because in our case, because this is a continuous function, fxy and fyx are actually equal. So that is why we have got this one. So see, this is a symmetric matrix. Whenever we have symmetric matrix, we can find the whether it is a positive definite or positive negative definite or all other things that we have discussed earlier. So for positive definite, we have d1 greater equals to greater than 0, d2 greater than 0. D2 means the principal minors of order 1, principal minor of order 2, principal minor of order n. So in this case, our these two is sufficient for our case. Now, so just to recall, it is negative definite if d1 is negative and d2 is positive. If we have a order 2 by 2 case. So yeah, the saddle point that you have, if you remember, the sitting place over the horse riding case. Okay, the person is sitting on a saddle. So this is a beautiful application of saddle point that here it is increasing. Okay, but if you go from there, it is decreasing. In this side, it is decreasing. In this side, it is increasing. So that's a beautiful, actually, application. Here it is increasing this side. They are decreasing. So that the red dot, this one is actually the saddle point for this case. Now, similarly, when we call for several variable functions, a minimum point or a maximum point. So first we will define, because for the several variable functions, the global maxima or the global minima is difficult to find. So that is why we will be interested in finding the local minima or local maxima. So if you remember the definition, the point a comma b is called a relative or local minimum if the functional value at f of a comma b is less than all other values, less than or equal to, in fact there also you can say less than or equal to. Okay, in fact if you remember the first definition, here also you can write, I have been talking about strict minima and strict maxima. Here also you can write less than or equal to. So there is nothing wrong writing strict less than. So just to recall, stationary points where derivatives is 0 can be divided into 3 points. One is maximum point, another is minimum point, and third one is saddle point. Now we have seen that if it is a maxima in one variable case, in that interval, so minus epsilon to epsilon, in this interval it will satisfy that either one f of x less than or greater than f of x naught, or f of x less than f of x naught. If this is a maximum or minimum point, these two inequalities holds. But what will happen if we have a two variable case? For example, this is a two variable case. This function is z equals to f of x comma y. So this surface. Now here we will here the point is actually a comma b type. Now whenever we have a point on the plane, point on the plane, then we can go to this plane by infinite number of paths. So that is why it is actually considering this whole, the neighborhood of this, actually this one. So for this point, so that is why in this neighborhood it will satisfy this relation. Similarly for local maximum, it will satisfy this relation. So that's the idea of local maxima and local minima for several variable function. So that's the definition. Now as you can see that geometrically saddle point is neither maximum nor minimum. So whenever we have a maximum case, so you can say this is concave downward, right? In fact, this function is also known as concave function. This function, and this type of function will be known as convex function. So whenever we have this type of function, we get maxima. Here we get minima. Now, just to again another thing we have to recall that what is the meaning of the partial derivatives on the plane on the surface. So, if you remember, this is the slope of the tangent along the y-axis. So, Fy. Similarly, this is the slope of the tangent line in this along the x-axis, and we have seen this is for z equals to f of x y. Then, if you try to define, so this is called a gradient. In fact, you have probably you have studied these things in the school level mathematics. If you have not, then the gradient of f of a, f of the gradient of f at the point x equals that a comma b is defined as this form. You find out the derivatives and evaluate that point. Now, if you remember, for single variable case, if you want to find out the stationary point, we have made f of x naught equals to, or particular case, f of x dash equals to 0. But here, if you want to find out the minimum point, then we have to make it 0. If we can get it, then we can say that this a comma b is a stationary point. Whether it is a maxima or minima, that will define that. For that case, we have to study something more. But in that case, let us we'll discuss. And if you write it in terms of vector, a vector v as a column can be written of this form. Similarly, this gradient vector, okay, can be read as gradient vector. Gradient vector can be written as of this form. So this will indicate one particular direction, and this direction is actually the perpendicular direction to the. If you uh, draw one tangent plane here, and this tangent plane contains these red lines. Okay, these red lines are on this plane, and this particular vector is actually perpendicular to the surface. Now there is the surface actually. If you say the perpendicular to the surface, that is mathematically not defined. So what it can be defined, if you draw one tangent plane on this line, and this vector will be, this gradient vector is perpendicular to the tangent plane. Similarly, this tangent, the perpendicular to the surface will be like this. Okay. So this is gradient of wave, gradient of wave, this gradient of wave. Now when this is 0, that means this plane will be parallel to the xy plane. And the application of this gradient you will find out here. If you try to climb up the hill, or if you go down to the bottom of the valley, then you will try to calculate what will be the fastest route and the fastest path to go down to the bottom of the valley. So minimum point, here it will be maximum point. So there we will try to find out the slope. Here the slope, if you plot here the tangent plane, here you plot the tangent plane, and this way you will find out the what can be the shortest or fastest route. That's a different actually discussion. Now, if you remember, this gradient is actually where is the minimum point, where is the maximum point for this function. You can see here, if you move this tangent, this dot point, if you move it, then you can see that these values are changing continuously. Okay, and then if you go down, and then you can see the change, rate of change, you can see so here delta h is the gradient vector, and it is this delta h with respect to t is also changing, this value changing, and this is also changing as we change the position of this point. Okay, so let us define the first order necessary condition. If we want to find out the minimum point for a several variable function, for example, two variable function, then the partial derivatives must be zero. So this is a necessary condition. Okay. In fact, when you will study machine learning or data science, they will start with these conditions because it is all about optimization, finding the maximum or minimum. So this is first order necessary condition. So the gradient should be zero. If you, and after this you will try to solve or find the values of a and find the value of b. So if you can find it, then you can say whether this a and b, whether it is a maximum point or minimum point. For that you have to understand the second order sufficient conditions. So which are this? So second order sufficient conditions are, for that you have to calculate the second order partial derivatives. So let us calculate the second order partial derivatives. Okay, and we call them as R, S, and T. So this is a symmetric matrix. Okay, and calculate the determinant. So RT minus S square. So first you have to verify whether it is greater than 0 or not. If it is greater than 0, then you need to find out another condition. If R, that is this quantity, is greater than 0, so both are 0, then you can call it a relative minimum. If this is a common condition, okay, and if R is less than 0, then you can call it a maximum, relative maximum. So this condition is known as second order partial, second order sufficient condition, because this will guarantee that the function having uh, either maxima or minima. But if this is 0 or if it is negative, further investigation is needed. No conclusion about an extremum can be drawn if the determinant is 0. In that case, further investigation is needed. On the other hand, if this is negative, then the function has neither minimum nor maximum at this point. So in this case, the point will be a saddle point. Now, if you remember, for a symmetric matrix, we can find whether this is a positive definite, if it is a negative definite, or indefinite. Okay. So in that case, we have saddle point. Something is, in fact, d2 greater than 0 and d1 less than 0. Or in fact, it can be also in this form. Here d2 is negative and d1 can be positive. So indefinite case will be like this. Okay, so this is the case. If you remember, also the convex, if you have the matrix, this H matrix, Its name is actually Hessian matrix. Hessian matrix and the Jacobian are very important two concepts. Okay, so Jacobian is first order partial derivatives. It is related to first order, and the Hessian matrix is second order partial derivatives. And whenever we have positive definite, this will indicate the function is convex. Whenever we have negative definite, the function will be concave of this form, and this is of this convex function. So you can say that from the matrix theory, we have this positive definite and negative definite. And here also calculus, from calculus we can see there is a connection between the linear algebra. So matrix theory and this calculus will have are very closely related in this respect. Now, what are the working rule for finding the extremum values? So first we need to calculate these five values. In fact, another condition can be del 2f and del y del x. We will be solving continuous functions and differentiable and continuous functions. So in that case, these two will be actually most of the time we will have they are equal. In most of the functions that we will deal will have this equation satisfied. So in order to find out the stationary point, we have to make them zero, first order derivatives as zero, and solve the equation, get the value a comma b, get the values of x and y. Then we have to evaluate the second order partial derivatives and evaluate at the point the stationary points. Now verify if this is greater than 0. If the determinant of the principal minor of order 2, if it is greater than 0, then we have two conditions, two conclusion. That is, if fxx less than 0, then we have maximum. And if fxx is greater than 0, then we have minimum. But remember, we have to first calculate the determinant of the Hessian matrix. But if it is negative, then no extremum values. That is the saddle point. And if it is 0, then further investigation needed. So these are the 6 basic steps to find out the extremum values for the given several variable functions. For this function, let us try to calculate fxy is given as x square plus y square plus 6x plus 12. Okay, now if you try to plot this function, it will look like of this form. As you can see, this is a convex function, concave upward. So here you will get a minimum point. Maybe here, this is the case, a comma b. But this, if you don't have any a graphical tool, then you cannot plot this type of diagrams. So these are actually three-dimensional plotting. But what you can do, you can always find out the analytical form. Del f del x. This is 2x plus 6. Then you can find del f del y. This is 2y. Again, you can find del 2f del x2. Here you have 2. And here you can find del 2f del y2. This is again 2. Not only that, you need to find out del 2f del x del y. If you find out here, so this becomes 0. Similarly, if you try to find out del 2f and del y del x, again this becoming 0. if you differentiate with respect to del y again, okay, then you will get this relation 0. So if you make, so the gradient of f xy, let us make it 0. So this will give you del x del x del f del y, make it 0. That means 0 comma 0 0 0. This is going to be x equals to 2x plus, here we get 2x plus 6 equals to 0, and here we have 2y equals to 0. So from there, here we can get x equals to minus 3, y equals to 0. So here we get x equals to minus 3 and y equals to 0. Okay. Now you try to, so only one stationary point. Minus 3 comma 0. So this is actually this is x positive direction, this is y positive direction, this is negative x, this is negative y, and this is it. So in fact we are viewing it on a two-dimensional shape. So this particular point would be called actually, in fact it is over this point. This minimum is over here, not there. Okay, so this function will be, so this is minus 3 comma 0 on the xy plane. Okay. Now we have to find out whether it is maximum or minimum. For that, let us try to calculate the Hessian matrix. fxx, fxy, then fxy, and then fyy. What is it? fxx we have calculated, it is 2. fyx 0. f again yx equals to 0, and here we have again 2. So the determinant of Hessian, that is r, if you remember, r into t minus s square. What is it? 4 minus 0. So this is 4 greater than 0. So the first condition is satisfied. So the point can be either maximum or minimum. But here we can see that fxx, that is r, is greater than r equals to 2, greater than 0. So by the second order sufficient condition, SOSC, by the second order sufficient conditions, we conclude that fx comma y has a minimum value at minus 3 comma 0 at the stationary point, and the minimum value is, so this is x cube, the function was x square, so minus 3 square plus 0 square plus 6 times minus 3 plus 12. So this is nothing but this is 9 minus 18 plus 12. So this is 9 plus 9, sorry, 9 plus 12 is 21, and then negative 18. So this is becoming 3. Hence, final answer, minimum point is uh, minus 3 comma 0, and f minimum is actually 3. So that's our final answer. Now again, if we try to solve this function, so it is actually depending on a. A is a constant or variable. If we change the value of a, then let us try to look at the diagram first. I have taken some help of the graphic tool. So if the value of a is minus 1.5, then the function will look like of this form. So try to find out that the function will have a minimum point or maximum point. That is actually, that will depend on the value of a and the point that we consider. Okay. See that the peak point or the valley point is actually on the, either it is on the negative, actually two coordinates. Out of the 8 octant, if you look at the uh, three-dimensional figure, you will have 8, like in two-dimensional case we have 4 coordinates, right? First quadrant we can say, but in place of this what is it called, three-dimensional figure, we will have 8 octants. These are called 8 octants. Okay, so there are actually 8 octants. We call them octants. So here it will be plus, plus. For example, this is plus, plus, and plus. There we will have some plus, minus. All the combinations will be there. Okay. So let us try to solve. We try to calculate fx. This is nothing but 3x square minus 3a into y. Then fxx 6x minus 0, that means 6x only. Then we calculate fy. So 3y square minus 3ax. So we calculate fyy. So this becomes 6y. Not only that, we need to calculate fxy. So you differentiate with respect to y, then it becomes minus 3a. And if you calculate from fyx, again you get minus 3a. So these two are equal, so we don't have to worry about it. Now the gradient, the first order necessary condition. By first order necessary condition, we have gradient of f x comma y equals to 0. So this will imply fxx fyy goes to 0 0, not goes to, actually equal to. So this will indicate that 6x, not 6x, this is 3x square minus 3ay, and then we have 3y square minus 3ax. Both are 0 comma 0. So we need to find out the values of the stationary points. So 3x square minus 3ay equals to 0. So from here you get 3x square. So 3 gets cancelled. X square equals to ay. And again we have 3y square minus uh, what do you call it, 3ax equals to 0. So from here 3, this 3 and this 3 gets cancelled. So y square equals to ax. So let us try. A equals to you get here x square by y. From here you get a equals to y square by x. If you equate them, then you will get okay. So let us write. Yes, that is okay. But yeah, here it is. A equals to x by y square. So if you equate them, then you get x square y equals to x by y square. We need to find out in terms of a. Okay, so let us not do that. We'll substitute the value of y in the other equation. So from here we get y equals to x square by a, and we'll substitute it here. So you will get y square equals to, this is in place of y, x square by a square, square, then a to x. So you will get x to the power 4 by a to the power 4 equals to a next. Tell me. Oh, right. Yeah, right. Right. Thank you for correction. So you can cancel one x. Now let us x to the power 4 minus a cube x equals to 0. So from here x times x cube minus a cube 0. So x equals to, you get 0, and you can write it in terms of the other x into x minus a, and then x square minus 1, but this is plus ax plus a square equals to 0. So from here you get x equals to 0 and x equals to a. So you have to find out, if you substitute x equals to 0 and a equals to a, then you get the y value. So x equals to 0 implies y equals to 0, and x equals to a implies y again a square by a, that means again a. So the stationary points are 0 comma 0 and a comma a. Now we have to evaluate the Hessian matrix. So that Hessian matrix fxx, that means for R, and here it is S, S and T. The determinant Rs minus T square, sorry, RT minus S square. So let us try to evaluate them. So two stationary points, these are 0, 0 and a, comma a. R value is at this point because R we have calculated fxx, we have calculated as xx. This is 6x. A's value we have calculated fxy, we have calculated it as minus 3a, and t value we have calculated fyy 6y. Okay. Now the a's value we have calculated minus 3a. So minus 3a will be at the both point. And it is not dependent on xy. So these values are actually equal. And t value at 0, 0 will be 0. Okay. If you put y equals to 0, then it will be 0. X equals to 0, then 0. So similarly, we will calculate the other point also. So here we have 6a, and here we have 6a again. So in this case, RT minus S square, here it is greater than. So first we have to calculate this greater than RT minus S square. If this is greater than, then what we have to find out? This one R. Whether it is positive or negative, based on that we have to decide. Since this is negative, so there is no extremum, neither minima nor maxima. So this is a saddle point. 0, 0 will be a saddle point. But this point a comma a is a point of minimum because this is 6a is greater than 0, provided a is greater than 0. In fact, we should have mentioned that a is greater than 0 because if a is negative, then the point will come here. So that is why this point should also mention a greater than 0. In fact, if you look at that, this is y direction, this is x direction, and this particular point is a comma a, here it is. Okay. And this particular value is actually minus a cube. For a equals to 1, you get minus a cube because the minimum value will be minus 1, and the point will be 1 comma 1, and 2 comma 2, at 2 comma 2 it will be minus 8. The minimum value will be minus 8, and this way you can find out. So these two are actually some working example, worked out example. Now I am giving you to verify these results as an exercise. Verify these results. Okay. We may have 1, 2, 3, 4 stationary points. You have to verify. You have to strike out where are the whether these are actually maximum point or minimum point. Now, whenever you have less than type, so you cross out. Whenever you have greater than type, you have to consider if R is greater than 0, then we have relative minimum, and if R is less than 0, we have relative maximum. So in this case, minus 7 comma 7 is actually a maximum point, and for this case we have a minimum point. In fact, this is mentioned in here also. For this function, show that this is a maximum point and this is another minimum point. So for that, you have to calculate all the steps. For that, you have to verify. Now, a sufficient condition for a critical point. Critical point, that means it is actually sometimes it is called stationary points are also called critical points. Okay. These are actually sometimes called critical point also. So these are just to remark. Nothing. This is not a remark. In fact, these are both actually same. In fact, we don't need to mention. Just to recall, I think I should call as sufficient. This is remember, not a remark. Remember this. So these are the tasks you can verify. Now another approach is there, another form of the second theorem, that is sufficient condition, that we have discussed. So let us just quickly recall. Let us just quickly mention and what are the things actually. So some textbook they prefer to call it as a positive definite. In terms of this sufficient condition, they want to mention it as a definite matrix form. So if this matrix is positive definite matrix, so positive definite means d1 greater than 0 and d2 greater than 0, right? Negative definite means d1 is negative and d2 is positive. Negative definite. So if it is a positive definite, then we will have minimum. Let us say PD. That is related to minimum. If it is negative definite, that is related to maximum. So if it is a positive definite, then the function is convex. If it is negative definite, then the function is actually concave. So everything is actually connected to each other. Okay. So another form, the function fx is has a relative minimum or a relative maximum at that particular point a comma b. If the matrix, the negative of a, here the Hessian matrix defined as this, if the negative of it, okay, it is another statement. But if you remember only one statement, that is sufficient. But this is just for your information. That if you multiply it with a negative sign, then the condition will be like this. So this is same principal leading minus or this kind of. So these are positive. B is a positive definite. Obtain these conditions in this way. Now it can be generalized to 3 by 3 case. So this is this particular point, the critical point or the stationary point is a relative minimum if A is positive definite. That means all the fxx, fyy and fzz are positive. You remember the positive definite matrix? So that means d1 greater than 0, d2 greater than 0 and d3 greater than 0. But if we have negative definite, what we see? D1 less than 0. Alternately, it will become D3 less than 0. So negative definite. In other words, it is saying in this sense, it is a relative maximum if the negative of this A is a positive definite. In fact, you can say in this way also. That means if you multiply with -1, you will get this, right? minus 1 it will become. So for example, if you try to calculate the maximum or minimum value for this function, first you have to find out the critical points. So the critical points are this one. There are several critical points, and you have to find out these relations whether both all are positive or not. And RT minus S square, you calculate them. Now you have to verify at these points 0, comma 1, 0, comma minus 1, we have greater than 0 and R greater than 0. So therefore, these points are actually relative minimum. Okay. And the minimum value you have to find out if you just substitute these values. So it will be minus 1. But if you look at the other points, you will have a relative. These points are actually relative maximum points. So the value is positive 1. But 0, 0 is the 0, 0 and 1, comma 1 or plus and negative 1 and negative 1, comma. These are actually, so this is RT minus S square is equals less than 0. So this is stationary point, not stationary. These are actually saddle points, neither maximum nor minimum. So we may have this situation. There are several points, and in fact, also again, I'd like to keep it as an exercise. Verify these results. This is actually related to next class. Now here you can find out for three variable case you can find out fxx, fyy, fzz, and then fxy, fxz, and fyz. You try to find out the Hessian matrix of order 3. That is the matrix of second order partial derivatives. So at 0, 0, we cannot conclude, but we have this matrix here. We need to calculate M1, that is the D1. In our case, we have defined it D1. Then M2, this is D2. Here it is D3, M3. So if you try to calculate the stationary points at this, whenever you take, whenever two coordinates are having same sign, okay, then this M1, M2 and M3 will be positive. If you think, because minus 1 into minus 1 will be plus, so in that case we will have this case. So these points are actually positive, positive definite matrix. That means the function will have minimum point. Whenever positive definite, so remember, positive definite is related to minimum. Negative definite is associated to maximum, or you can say relative minimum. Let us say local. And this is local maximum. And what will be the value? Just substitute the value. Okay, just substitute the coordinates at that point. You will find out the value. So again, there are some practice problems. So try to find out, verify these results, whether they have functions or maximum or minimum. Try to find out the results. So with this, I will stop here today. If you have any doubt, you can ask me.